Welcome to this elementary statistics lesson on the one-sample z-test. In this lesson, we will walk through an example of how to use the one-sample z-test. The one-sample z-test is a test for a sample with known standard deviation. The following information must be known to use the one-sample z-test: the sample mean, x, the population standard deviation, sigma, the sample size, n, and the fact that the population is normally distributed. Imagine that you want to determine whether zebras living in one region of a country, region A, weigh more than zebras living in another region of a country, B, due to the difference in water availability between the regions. You hypothesize that zebras in region B, due to unexpected flash droughts, drink more water and try to remain in a better state of hydration than those in region A. Most studies have been performed on zebras from region A, and their weights are known to be normally distributed with a mean of 500 pounds and a standard deviation of 33 pounds. You take a sample of 10 zebras living in region B and find that the mean of the sample is 507 pounds. Are the means of the two groups of zebras different at a 95% confidence level? First, ask yourself whether you have all of the information you need to perform a z-test for this hypothesis. Remember that you need to know the sample mean, x. In this case, we do know this. We know that the sample mean is 507 pounds, and we're comparing this to a population mean of 500 pounds. We know the population standard deviation, 33 pounds, and we know the sample size, n, is equal to 10. We also know that the population is normally distributed. So, we can use the one-sample z-test. Let's formulate our hypotheses. The null hypothesis is that region B zebras have an average weight that is the same as or less than that of region A zebras. This is because we are hypothesizing, or in our research hypothesis, that the zebras in region B have a greater weight than the zebras in region A. Thus, the null hypothesis is mu B is less than or equal to mu A. So, write down the research or alternative hypothesis. Since the null hypothesis is that mu B is less than or equal to mu A, the research hypothesis is that mu B is greater than mu A, or that region B zebras have a greater average weight than region A zebras. Now calculate the test statistic. The formula for the z-statistic is given below. The z-statistic is calculated x, the sample statistic, minus delta, the population statistic, divided by the standard deviation of the population, divided by the square root of n. So, the z-statistic is 507 minus 500, divided by 33, divided by the square root of 10, or 0.671. Knowing that the test statistic is 0.67, look up the cumulative probability in a z-table and compare to the cumulative probability for a 95% confidence level. First, determine the z-score for a 95% confidence limit. A z-table is shown here. Recall that the rows give the first and second digits of the z-score, while the columns correspond to each of the 10 possible digits for the third digit of the z-score. This is a one-tailed test, so the z-value is that for which the cumulative probability is 95%. We look in the table for a cumulative probability of 95%. A cumulative probability of 95% corresponds to a z-value of 1.65. We can tell this by looking up 95% cumulative probability, or the value closest to it in the z-table, and finding that the corresponding first two digits for the z-score, the row value, is 1.6, and the corresponding hundredths digit, the column value, is 0.05. Adding these together, we get 1.65. We know that the critical z-value is equal to 1.65. This is greater than our z-value, so we have not reached a 95% confidence level. Let's determine the confidence level by finding the cumulative probability associated with the z-score of 0.67. The first two digits for this z-score are 0.6, so find the row that corresponds to 0.6, and the column that corresponds to 0.07. The corresponding cumulative probability is 0.7486, or approximately 75%. Given the test that was conducted, calculate the 95% confidence interval about the mean. Remember that confidence intervals are two-tailed. There's an alpha over 2 probability above or below each of the upper and lower confidence limits, respectively. The confidence interval is calculated using the formula shown. The lower confidence limit, A, and the upper confidence limit, B, are equal to X, the sample statistic, plus or minus the z-score associated with 1/2 alpha, multiplied by the standard deviation and divided by the square root of n, the sample size. We know that X is equal to 507, sigma for the population is 33, and n is equal to 10. Let's look up the z-score corresponding to alpha divided by 2, or 1/2 alpha, in a z-table. In this case, alpha is equal to 0.05, so alpha divided by 2 is equal to 0.025. Using a z-table, we can determine that 1/2 alpha, the z-score corresponding to 1/2 alpha, is equal to 1.96. And we'll plug this value into the confidence interval equation. Let's practice using the z-table one more time. Remember that the values in the table are associated with the cumulative probabilities. The z-score associated with alpha divided by 2 is the z-score associated with a tail value of 0.025, or cumulative probability of 0.975. Finding this in the table, we find that the corresponding row value for the z-score gives the first two digits, 1.9, and the column value gives 0.06. So the z-score is 1.96. Now plug these values into the confidence interval equation. Doing so gives X, 507, plus or minus 1.96 times 33 divided by the square root of 10, or 507 plus or minus 20.5. Thus, the 95 confidence interval about the mean is 486.5 to 527.5. What would be the sample size needed to determine the average weight of region B zebras plus or minus 5 pounds with a confidence level of 95%? Remember that for a confidence interval, we had an interval of 486.5 to 527.5. Because of this, we were not able to discern whether our region B zebras were different than our region A zebras in weight, because our region A zebras averaged 500 pounds. 500 pounds was within the 95% confidence interval. However, if our confidence interval were only plus or minus 5 pounds, the 500-pound weight of the region A zebras would clearly be less and outside of the 95% confidence interval of the region B zebras, whose average weight is 507 pounds. We calculate the sample size using the formula shown. N is equal to 2 times Z corresponding to alpha divided by 2 times sigma divided by W, the width of the confidence interval, all squared. Do we have the information we need? We know the standard deviation, sigma, is 33 pounds. The confidence level desired, alpha, is equal to 0.05 because this is a 95% confidence interval. The confidence interval width desired is 10 pounds because we're interested in a plus or minus 5 pound range. And the z corresponding to alpha over 2 is again the z corresponding to 0.975 or 1.96. Plugging these values into the equation gives 2 times 1.96 times 33 divided by 10, all squared. This value is 167.34. We always round up, so 168 participants are needed. This concludes our z-score example. In order to master using z-tests, which is vitally important in elementary statistics, make sure to practice all practice problems and to watch this video as many times as necessary to understand each step of the process. Although this information can be a little overwhelming at first, if you watch this